Hello, it's Sean Allen, AP Calculus student, and welcome to today's video. Today we're going to be talking about the mean value theorem and how it applies not only to the calculus world, but into the real world where we can use it to figure things out. So first things up, exactly is the mean value theorem? Well, many of you may know this, but the mean value theorem is formally defined as stating that f of x is defined and continuous on the interval from a to b, and differentiable on that same interval, then there is at least number c in that interval such that a is less than c, which is less than b, and that is able to give us f prime of c equal to f of b minus f of a over b minus a. Now that might sound very complicated, but it's really not. It's not very scary at all. First, we have our normal mean value theorem definition. It's our standard equation that we will use in all of our calculating with mean value theorem. And what that really comes down to is finding the slope of a function m. Now you might ask me, how is that possible? Well, there's another way to notate m. You can notate m like this, or you can notate m like this, delta y over delta x, which if we're using b and a as points on a function, well, b minus a is delta x, and f of b minus f of a is delta y, the same thing. So let's try a practice problem. This is a pretty easy practice problem. Problems like this will sometimes pop up on the AP Calculus exam, so let's do a practice, try to get prepared for that. So let f of x equal x cubed plus 6x squared plus 6x. Let c be the number that satisfies the mean value theorem for f, the function, on the interval -6 to 0 inclusively. What is c? For those of you who want to really try this, I'm going to give you a second, give it a shot, and we'll see you in a second. Alright, are my triers done? Well, actually the answer to this question is the second answer, -4. And here's why. So we have our function f of x equals x cubed plus 6x squared plus 6x. And f prime of x equals 3x squared plus 12x plus 6. So f prime of c equals 3c squared plus 12c plus 6. And now that we have our f prime of c, we can set that equal to our mean value theorem equation. But first, we need to recognize that our interval is from -6 to 0, so we'll make a -6 and b 0. When we do that, we have our basic f prime of c, 3c squared plus 12c plus 6. We're going to set that equal to f of b minus f of a all over b minus a. And when you calculate it out, you get this. 0 minus -36 all over 0 minus -6. And when we calculate this out and solve for c, we get c is equivalent to 4, or -4, excuse me, and 0. And since back on our multiple choice problem, -4 was the only answer choice available, that was one of these two, -4 is our answer. Anyway, moving on. Here is some data I was able to collect from ourworlddata.com. You can see their little logo there in the top right hand corner. And this was the average height of men by year of birth from 1820 to 1980. So the average height of men over the decades. And here on your top left is some tables I've been able to put together using this data that show what the height is in centimeters. And so for our American viewers, I placed some equivalent in feet height measurements on next to our graph there. And then here on our bottom left is just a really cool graph I found, just average height of men across the world in 1980, that were born in 1980 rather. So that's really cool to check out. Well, anyway, that's really cool and all, but what can we really do with this data? Well, first things first, one thing that we could possibly do with this data is here in the blue with the highlighted dots is our data point. That's very similar. It's actually the exact same as the last graph, and that red line, our function rather, is a estimated function for it. And as you can see, it's pretty close. I just wanted to show you guys that. But what can we really do with this data? Now, the big thing that we can do with this data is we can use the mean value theorem to calculate the average rate of change of men height within a certain time period. And so what I challenge you guys to do is do it by decade, so using years from 1820 to 1830 and then 1830 to 1840, and go ahead and give that a shot. I'll leave the table up here, and if you guys want to give it a try, I'll give you a second to get that ready. Alright, we done? Well, here are the answers I calculated. Here on the right in the chart is notated as year and average rate. I used the middle year of each decade period to indicate which interval it was on. And here on the left is the graph of my answers. In green are the exact points, and the orange is the function that I'm using to just kind of estimate it / correlate it, because a lot of times in calculus you'll need an exact function. But anyway, here's how I did that. So basically what you got to recognize is you got to recognize what your variables are. So here I put A is equal to 1820, B is equal to 1830, f of A is equal to 172.2, that's in centimeters, and f of B is 173.5, also in centimeters. And so after that, you just got to plug it in your formula, and what you get is from years 1820 to 1830, the average rate of change for men was 0.13 centimeters per year. And that's really cool. Now that we've calculated stuff like this, what can we really do with this type of math? Well, there's a lot of things we can do. In the example I provided, using the male height in America specifically, we can take historical data, since we are given time periods, and try to figure out maybe some environmental factors that have played into the changing height of men and humans in general, such as the advent of electricity, processed foods, and other such commodities. Honestly, though, there's so much stuff that you can do with calculus, and I hope, if anything, that you've learned today, it's not only a little quick review on the mean value theorem, but also that with a little bit of data, a little bit of math, we can take steps to better understand the world around us. And that is the mean value theorem, and I hope that's helpful.